So what I just explained for non-uniform learnability, essentially in practice, in many cases we face many different types of hypotheses. Some hypotheses are very simple, some hypotheses are very complicated. So the required number of training samples are very different for different hypotheses. And sometimes we can utilize some prior knowledge on each hypothesis class. If we know this hypothesis is very complicated, then we naturally know there could be more difference between sample error or the training error and the test error. Or if we know this hypothesis class is very simple, then we can easily guess, okay, the training error and test error will be very close. Structural risk minimization is kind of technique that utilizes such prior knowledge. So how to encode our prior knowledge, especially on hypothesis. So let H, the hypothesis class, include a good predictor for the learning task, which is our prior knowledge. Usually the hypothesis class itself is the prior knowledge we use, because there are really infinitely many number of different functions, and each function can define input and output pair. But restricting a class of hypotheses means we will ignore many unnecessary functions which are very unrealistic from our learning process, and we will only focus on this set of the set of hypotheses, because we know that very nice prediction will located inside of this hypothesis class. So the hypothesis class itself is our prior knowledge. In addition, we can specify preferences over hypotheses. Okay, although two different hypotheses belong to the same hypothesis class, they could be different. One might be more preferred compared to others. That is also possible. So from now on, we assume that the hypothesis class consists of many different hypothesis class. So that is a union of many different hypothesis class. And we know a weight function W that assign a weight to each hypothesis class HI, such that a higher weight reflects a stronger preference for the hypothesis class. So W function, that is kind of our prior knowledge over hypothesis. Okay, hypothesis set itself is one of our prior knowledge. In addition, we can specify preference over hypothesis, which will be defined by this weight function. The weight function will give us some prior knowledge, and the prior knowledge will control the learning process. Okay, so to understand the structural risk minimization, shortly SLM, I'm gonna introduce some definition. For each I, the class HI has the uniform convergence property with a sample complexity function this. And for a given n, we define a function of epsilon. So for given n, there is corresponding epsilon for given n and delta. So we denote by epsilon I, n and delta, which is mean of epsilon, the smallest epsilon that satisfies this. Okay, we can guarantee epsilon amount of divergence between training and test with probability 1 minus delta when we have n number of training data point. And let W, which is a weight function, and we assume that the W function is normalized. Normalized means the sum of Wi is upper bounded by 1. So for union of finite M hypothesis class, we can simply use 1 over n, which means there is no prior information over hypothesis class. But there are many other very useful hypothesis, very useful weight function like Wi is equal to 6 over pi square I square. So when you search Bessel problem, you can easily know that the sum of such Wi is equal to 1 when I want to infinity. Or W1 is 2 to the minus I. This also the sum of 2 to the minus I is equal to 1. So they are very nice form of weight function examples. So when we sorting our hypothesis class from the most likely one to the worst one, kind of, and then use this type of weight function, we can easily satisfy this and we can give more weight to more favorable one. Okay, so this is the pseudocode of SLM algorithm. The prior knowledge is our hypothesis class. We first define hypothesis class and we classify each hypothesis into several different categories, H1 to H1, H2, extra. And for all I, sample complexity function and HIUC will be given to us. And thus from this one, we can also know what is epsilon I function. Epsilon I is function of delta and n. And the weight function also given to us. So all prior information are like this. And from that we define IH. So because there could be some overlapping between HI. Let's say for a given hypothesis H, the corresponding hypothesis class index I is the minimum of I among hypothesis class H belong to. Okay, so we will use the smallest index among the members, among the membership class. Okay, so input is of course the training set and confidence bound confidence level delta, and then the output is this. We will find the best hypothesis that of course minimize the training error, but we will not just use training error, we will add something which is kind of confidence interval. So for the given training data point with the weight and the confidence level delta, we calculate the epsilon. So this epsilon function will upper bound our true test error minus the training error absolute value is upper bounded by epsilon I h with probability 1 minus W I h, the weight function, times delta. So this is kind of upper confidence bound. So we will discuss such UCB, upper confidence bound, when we study banded algorithm for the next part of our course. But this is very nice indicator to select best hypothesis. Since we consider such an uncertainty to select the best hypothesis, this gives us very nice hypothesis that guarantee some nice guarantee of performance. Okay, so this is the theorem 7.4. Let W be a weight function we are considering, and H be a hypothesis class such that hypothesis H is a union of a different class of hypotheses, and every HI satisfies the uniform convergence property with a sample complexity function and HIUC. Then for every delta and distribution D with probability of n is 1 minus delta, the following bound holds for all I and H. Following bound is this. So this can be shown using union bound very easily. The proof use this. The event, there exists hypothesis H that has more than epsilon I generalization error is equal to the union of the event, there exists H in Hi, of which generalization error is more than epsilon I and Wi delta. Okay, and since each event probability is upper bounded by Wi delta from the union bound, the probability of this event is upper bounded by summation over Wi delta. And also we know that this value is upper bounded by 1. Okay, so this event probability is upper bounded by delta. So with probability 1 minus delta, we can say this for all I and H. So this is the SLM rule result. So basically when the number of sample complexity of non-uniform learnability, epsilon delta H hypothesis is less than or equal to the sample complexity function for uniform learnability for hypothesis set HIH for parameter epsilon over 2 and W weight function for the index IH times delta. This is because from the union bound with probability 1 minus delta, we have this result for all hypotheses in our consideration. Therefore, by the definition of SLM rule, we basically find the hypothesis. So the output of algorithm for the given training set S has the test error, which is upper bounded by every hypothesis training error plus the confidence interval from the SLM rule. Okay, so and also the from this concentration inequality or from this inequality rule, we also have upper bound of this training error. The training error is upper bounded by the test error plus epsilon IH, which means this value is upper bounded by the test error plus 2 times epsilon. So when we have the number of samples that satisfy epsilon over 2 times WIH times delta peng learnability, then for the hypothesis H, we have 2 times epsilon over 2 error generalization error bound. So we have the non-uniform learnability with this sample complexity. So the model selection, basically we usually consider Occam's razor argument. We prefer the simpler algorithm. So in machine learning, a simpler algorithm shows a better generalization, which is a common belief in machine learning field. So when we know the complexity of algorithm, we use weight functions so that the weight function give more higher weight to the simpler algorithm that support Occam's razor. So using the higher weight to the simpler algorithm, we can more likely choose simpler one because simpler one has better generalization property. So when we go back to the SLM rule, we basically add some confidence interval, and when we use smaller weight, this confidence interval, the part will increase. So even if the training error is very nice because we use very complicated algorithm, due to this part, we can choose simpler one. Okay, although simpler one has high training error, because the simpler one have very tiny confidence interval, we can choose simpler one. That's the Occam's razor argument. So the weight function and complexity has some correlation. So when we know the complexity, we can assign a higher weight to a simpler hypothesis so that we can consider such a trade-off. But we can think model selection in other way. So usually in practice, we select model using validation set. So assume that we have many different hypothesis class, and we want to find the best hypothesis among these many hypothesis classes. In practice, we separate our training data into 3 different parts: training and validation and test. Using training set, we train each hypothesis class independently. So each hypothesis class learn empirical risk minimization rule with the training data. Then for each hypothesis class from H1 to HR, we can find one single best hypothesis that has the smallest training error. But we don't know which hypothesis is the best, so which hypothesis class is the best among our different hypothesis class. So we cannot say which one is the best among these. So we usually use validation set to test H1 star to HR star, the selected hypothesis, so the representative hypothesis for each hypothesis class. So HS, the selected hypothesis, learn ELM rule again with the validation data. Okay, and using the validation data, we can guess the test error of each H1 to HR star, and then find the best one. Okay, the test estimate the final, and then we finally use the test set to estimate the final performance, the final selected hypothesis. But here we can define the pack learnability for the validation process as well. So here the validation set, using the validation set, we choose the best hypothesis among our different hypothesis set, which comes from different hypothesis class. That is also ERM learning. Basically, from the validation set, we compute the training error, validation training error, kind of validation training error for each hypothesis, which is each selected hypothesis, and then choose the best one. Right? So when the number of data points in the validation set is tiny, then again there is the risk, the difference between the estimated test error using the validation set and the true test error. So in some chance, with some probability, although H1 star has very bad training and very bad test error, but if we unlucky, H1 star is just good for the validation set. So we finally decide H1 star as our final outcome. That also possible. Overfitting to validation set also possible, especially when validation set size is small and when the number of hypothesis class is huge. That's why we have to use test set so that the selected hypothesis is really good for our testing. Especially when we design some deep learning network architecture, there are a lot of hyperparameters. Which means there are a lot of different hypothesis classes. R is very, very huge. So the test set is very useful, especially in deep learning models.